Okay. So, I have discussed about the radix 2 algorithm and divide and conquer method for implementing discrete Fourier transform and using FFT algorithm. Let us say you have known how to implement FFT algorithm. So, I know how to implement FFT algorithm, then what can I do? Let us say simple application that suppose I have a signal x of n, let us say I take the next slide. So, I have a signal x of n, I want to draw the spectrum of the signal. So, what is spectrum? The spectrum of the signal is nothing but a, when I plot, this axis will be the frequency and this axis will be the amplitude of individual component. So, let us say I converted x of n to x of k, x of using FFT algorithm. So, x of n is a discrete signal, using discrete Fourier transform implemented in using FFT algorithm, I converted to x of k with n point DFT. So, once I does that, I get x of k, k varies from 0 to n. I want to draw the plot, the frequency, this x axis will be a frequency, y axis will be mod of x k. This you have to do it by hand. So, what I said, let us say generate a signal x of n which has a frequency component or cosine frequency component, let us say 2 kilohertz and 3 kilohertz sampled with 8 kilohertz. Generate, let us say 1024 number of sample, compute discrete Fourier transform using FFT algorithm, then plot the mod of xk versus frequency or spectrum of the signal. So, how do you do that? So, what I will say, I have to generate, I can write down x of n equal to let us say 10 cos 2 kilohertz 2 pi f by fs plus 20 cos let us say 2 pi f1 by fs f2 by fs. So, f1 is equal to 2 kilohertz, f2 is equal to 3 kilohertz, I can get that x of n. So, n varies from 0 to 1023. So, n equal to 0, x of n equal to 0, n equal to 1 I calculate, program will calculate, n equal to 2 program will calculate. So, I collect that signal, then I compute n point DFT using FFT algorithm, I get x of k. Now, I have to draw. So, x of k is a complex number. So, what I get? I get the real part and imaginary part. So, mod of x k is nothing but a real part square plus imaginary part square. So, I can easily do that. X of k is a complex number, I can real square plus imaginary square, I get the mod of x k. Now, how do I get the frequency? So, if I draw k versus a mod of x k, I know k equal to 0 means this one, k equal to 1, 2, 3, 4 up to n minus 1 I will get. But k is discrete frequency, but I want to draw against analog frequency. So, how do I convert k to f? It is nothing but from the resolution. So, I know what is the resolution of this conversion, n fs by n. What is the fs? 8 kilohertz. So, 8 kilohertz by 1024 is my resolution. So, when I am multiplying with k equal to 0, then it gives me the f0, first frequency. Second frequency is 8 into 10 to the power 3, 8 into 10 to the power 3 divided by 1024 into 1. Third, 8 into 10 to the power 3 divided by 1024 into 2. Let us say it is considered approximately 10, so 8 hertz. So, first component 0 hertz, second component 8 hertz, third component 16 hertz. So, like that way I will get. Now, as you know, the discrete Fourier transform is in symmetry. So, whatever I will get n by 2 look like this. So, at n by 2, so instead of 1024 point, if I compute x of k up to 512 point, then I get this plot, and that is my spectrum. This and this is nothing but a mirror image. So, that is my spectrum. Now, see, my signal is a long signal. So, here I said generate 1024 point signal, and signal is stationary, because if I continue the signal, signal does not change its color, change its property. Now, suppose it is long signal with the stationary signal, long signal, and I want to process 1024, let us say I generate for 8,000 sample, 8,000, or let us multiply by 10, 10240 sample, and my length of the DFT is 1024. So, every time I cut the signal with 1024 point, if it is stationary signal, then overlap, add and overlap, same methods can be applied for when I convert to the inverse DFT. Okay. One important information I forgot to give you, the FFT algorithm is applied for discrete Fourier transform, this is applied for inverse Fourier transform also, because the algorithm is same. It is applied for not only the Fourier transform, for the discrete Fourier transform, it can be applied for inverse Fourier transform also. So, the algorithm will be same, only the Wn instead of minus it will be plus, or normalization factor 1 by n is added up. Okay. Similarly, so long signal I know. Now, if it is non-stationary signal, suppose I give you an example. Let us say I will show you a demo in a cool edit software. So, I have a signal. So, this is my speech signal. Let us say this is my speech signal. If you see, this is a speech signal I have recorded, although the signal is clipped. So, I am not going details on that. Let us say this portion of the signal, I can zoom it. So, this is my signal. If you see, the signal is non-stationary, the property of the signal is changing. This time it is noise, completely noise kind of things. This time, if you see, this time it is periodic, and this time periodicity also change. So, the signal is not time independent, so it is time dependent. So, in that case, if I take entire signal and take the spectrum, entire signal and take the Fourier spectrum, so what I will get? I get an average representation of the signal. That is not the correct analysis. So, suppose I want to know what is the spectrum representation of this portion of the signal. I select this portion. So, once I select the portion, I am doing short time Fourier transform. So, what is come into the picture? Window is come into the picture. So, if you see the analyze frequency analysis, I get the frequency analysis. Here hertz, this is the linear view, this is the non-linear log view. So, it is a linear view. So, this axis is hertz and this axis is the intensity in dB. Now, when I say that, then if you see, instead of line, I can those things is different. Let us say what is the advanced characteristics are there. Here, if you see, I can change the FFT size. If you change the FFT size, n is changing, but signal is remain same. Okay. So, the small portion they have doing. I can change the window, Hanning window, Hamming window, Blackman window. I can say that it is not linear view, it is log view, log spectrum. Frequency axis is in here, if you see, it is in log scale. or I can line graph. So, all those things I can do for frequency analysis of the signal. So, suppose I give you a target, that suppose I told you write and program to compute spectrogram of a signal. There may be a phase spectra. If you see here, there is two kinds of spectra is there. One is called phase spectra, another is called amplitude. This is amplitude spectra. If you see, go to analysis, so phase analysis, you can get the phase spectra. So, if I told you again, phase spectra is also same thing, left to right, mid to spin, you can say the spin. So, this is the phase spectra, normalize like that. So, those things are the graphical representation. So, suppose what is phase, what do you do the amplitude spectra and phase spectra. So, what is given? The signal is given which is also non-stationary. X of n is given which is non-stationary. So, I have a long signal, I select a portion, I want to the spectra. So, how do I select a portion? I multiply the signal with a window function. Okay. So, when I write, different window functions are there, as you know, Harris Blackman window, Hamming window, Hanning window, rectangular window, and I have described what is the effect of each of the window. Some of the window main lobe is very wide, width is very high, and side lobe leakage is less, but many times rectangular window main lobe width is less, but the side lobe leakage is very high. So, you know that I will not get the original signal spectra only, the original signal will be convolved with the frequency response of the window spectra. So, I implement this rectangular window. So, I first I get x of n, then multiply with w n, then pass through FFT algorithm which implemented the discrete Fourier transform. Let us n is equal to, let us say 512. Then once I get that, I get x of k varies from 0 to 512. I know I do not require the last portion. So, I can say the k equal to 0 to 512 divided by 2 is sufficient. So, I get, and then I take mod of x k, that means x k is complex number, I can take the real square plus imaginary square. So, x k is represented by a by j b. So, I compute root over of a square plus b square, and once I done that, I know the sampling frequency of the signal. So, once I know the sampling frequency of the signal, I said f is relations between the f and k, 2 pi is nothing but a fs by n into k. So, I know a k index, I calculate corresponding analog frequency. So, corresponding to that frequency, I pointed out the amplitude, corresponding to the frequency, pointed out the amplitude, you get the spectra. Now, say spectrogram. What is spectrogram? If I show you, so this is a time domain signal. If I draw this one, is called spectrogram. Let us say I zoom this portion. So, more yellow means more power, more prominent in the frequency, means those frequency has a high power. If you see, after I think this axis in spectrogram, this axis represent the frequency, this axis is representing the frequency, and this axis is representing the time. So, different time instant, what is the frequency composition of the signal as is represented by a spectrogram? You can see this is look like an X-ray plate. So, how do I do this? This axis, x axis is time, y axis is the frequency, and intensity or color of the image, the intensity of the signal can change, represent the color of the image. If I represent it in a purely black and white, then if I say the black, more black means more energy, more white means no energy. So, it will be, this portion will be white and this portion only have a black line. So, that is called spectrogram. But how do I do that? If you see here also, when I am doing the spectrogram, there is some setting. Window function, which window function, what resolution, how many bands you required, window width, 70% overlap. So, all kinds of setting you can do. So, suppose I told you write a program for computing spectrogram or representing spectrogram of a signal. So, if you see, I have a signal x of n, this axis is time I know, and the signals are there along the timeline. I want along the timeline frequency component has to be written down. But if you see, can I compute the discrete Fourier transform from sample by sample? Then if you see, if it is required, suppose these cases, in these demo cases, how many samples are there? In the signal, if I click it here, it has come to the samples. 1,42,368 samples are there. So, if I compute want to draw spectrogram by sample, it is take huge time. So, what I will do? So, instead of saying that I am taking the time resolution, let us say I take the time resolution, define an window. So, how do I define a window? Let us say I told that I will take 20 millisecond window, length of the window is 20 millisecond, and as if you know that there is a, to complete recovery of the signal or proper representation, there is some overlap is required. Let us say 50% overlap. So, windows, so I take 20% 20 millisecond signal with 50% overlap. So, if it is 1 second signal, then 20, how many frames will be there? So, this 10 millisecond is called frame 1. Then, so 0 to 10 is frame 1, 10 to 20 will be frame 2, 20 to 30 frame 3, but window is 20 millisecond. Why? Because if it is 10, suppose the signal is 8 kilohertz, sampling frequency is 8 kilohertz. Now, you know in 10 millisecond there will be only 80 sample. So, if I pad so many 0, then the spectrum will be not that correct, the frequency resolution will be problem. So, what I will do, I'll instead of 80 sample, I take 160 sample and I shift the frame by 10 millisecond. So, if I see the time axis, what will look like this? For every 10 millisecond, I get the signal. So, I am assuming that every 10 millisecond signal is same, signal is stationary. So, for this 10 millisecond, I get the spectrum. So, for that 20 millisecond signal x of n converted to x of k. Okay. So, this axis is my k, k can be converted to f. So, for this signal I get frequency response horizontally for different k. So, each of the cell represent frame numbers, frame 1, let us say k equal to 10 here. So, this is k equal to 9 and this is k equal to 10. So, this box basically represent this portion of the signal, the k equal to 9 to k equal to 10 frequency band. So, this is called band. So, how many k's are there? If my sampling frequency is 8 kilohertz and if the length of the DFT is n, I know resolution is 8 by n. So, each length is 8 by n, 8 by n, 8 by n. So, I can say those are the band pass filter which is 8 by n. So, how many bands will be there? If it is, you know, if the sampling frequency is 8 kilohertz, what is the signal content? 4 kilohertz. I only have to analyze up to 4 kilohertz, n by 2. Okay. So, k by 2, k equal to n by 2. okay, for 4 up to 4 kilohertz. So, how do I set k equal to 0 to k equal to n by 2. So, up to 4 kilohertz I want to know. And what is the resolution? Fs by n. And how many band will be there? If the Fs is 8 kilo, so 4 kilohertz by n is the number of by n is the bandwidth. Okay. So, n by 2 number of band will be there. N by 2 number of such band will be there, and each band bandwidth is Fs by n by Fs by n. So, if you see, when you see the spectrogram, it is not, and you can see there is a vertical line and horizontal line. Vertical line are corresponding to the time resolution, horizontal lines are corresponding to the frequency resolution. Is it clear? So, that way I can easily draw the spectrogram of any signal, spectrogram of any signal. Okay. So, this is the application, and also when we analyze the signal in frequency domain, spectral estimation, I will cover that part, spectral estimation. So, whenever I have to analyze the signal in frequency domain, whether it is single dimensional, whether it is two dimensional, it is nothing but I have to compute in 2 times. One is x axis, another is y axis. First I compute DFT, one dimensional DFT along the x axis, then for every x I will compute the DFT for, so row wise, then column wise. But algorithm will be same. One dimensional FFT algorithm will work in there also, but I have to compute in 2 times. Okay. So, that way you can apply this kind of knowledge. So, whatever I cover in this FFT this week, that how do I efficiently compute discrete Fourier transform. If you see, DCT can be represented by a discrete Fourier transform of 2n instead of n. So, if I implemented Fourier transform and if it is very efficient, then instead of direct computing of DCT, I can use this FFT also to compute DCT. So, FFT, what I said, pure fast Fourier transform, that is nothing but an algorithm to implement discrete Fourier transform or efficiently calculate discrete Fourier transform. Okay? Thank you.